maybe say accuracy and then recording. Okay, so maybe this is a lesson for all faculty members that we also can start slowly to build the machine and then do our research on that instead of always expecting that to buy the machines from outside. Okay, yeah. So with that addition, like I'd like to thank Dr. C.P. Paul again for his wonderful lecture. And then now it's a really great challenge for me as a next speaker for this talk to match with your presentation. I'll just try my best. Okay. Thank you, Dr. Subbu.
Thank you, Dr. Subbu. It was pleasure meeting you all guys on the virtual platform. Please do write to me for any other questions. I'll be happy to help you. I'll take this opportunity for you guys to invite to RRCAT for any of the project work related things. We'll be happy to help you in that way. Thank you very much.
Thank you, sir. Yeah. So I request the participants to hear for something because we have to fill the feedback. Yeah. Saravanan? Hello,
yes,
Saravanan?
sir. Yes,
yeah, please,
yes,
can
sir.
you share the feedback form?
Yes,
so
sir.
that,
Yes, sir. I'll share it now, sir.
Dear participants, like, yeah, I requested already that please join for the meeting with your name by which you have registered for this course, because we have to take attendance. Since sessions are going on, it is very difficult to take attendance in between. So we have some other mechanism to do that. Okay, so what I request is that please join for the meeting with your name, like real name or whatever you registered in the ATA website. Okay. Another thing is now we have shared the feedback form. Please fill this feedback form so that we will come to know about our maybe workshop, how it is going. So what modification we can do or what improvement we will do in future. So do you have any questions, please? We are happy to answer. Participants, do you have any queries? Please, as a coordinator, I'm happy to answer those questions. So we shortly will share one more Google form. Maybe you can fill your basic details with the photo and all those things so that we can have it for our record. Apart from that, end of this workshop, you have one test. So you know that as per the ATAL thing, you have to score minimum 60% and you should have 80% of attendance. So then only will get a certificate. So we planned this particular program in such a way that which covers from the basics to maybe the state of the art things in additive manufacture. Okay, so please interact with the experts so that will gain more knowledge. Apart from that, maybe we have like additive manufacturing group here also, in the sense like there are 4 or 5 faculty members are working in that area. Okay, so in future, if you want to have any like discussion, please drop an email to the people and then have a contact with them so that you can gain more knowledge. Yeah. So if you have any question, I'm happy to answer. Otherwise, we can take a break for 15 minutes. Again, we'll meet at 11:15. Okay, so I'm not going to close. This is the same link only you have to use for joining. Maybe meanwhile, I'll stop recording it. Then around 11:15 again, we'll start our recording. And then the next session will meet. Okay, no more questions. It's 11 o'clock. We'll take a break now. Okay. So if you want to keep your login as it is, no problem, because we have to join at 11:50.
Good morning, sir.
Yeah, good morning, Vijay Kumar. Please.
Sir, would it possible to get the PPT of this presentation, sir?
Doctor, I don't like. Yeah, Vijay Kumar, please. We are recording the session. Okay, then it will be like shared with ATAL maybe coordinator, so you can see the videos over there. So generally, it is very difficult to get the thing, because it's all like people are putting effort and then they're making it, and then it's not even professional to add them. So for
Okay,
reference
sure,
purpose,
sir, sure, sir.
obviously,
Even if it is a recorded session, that is okay.
sure it will be there. Sure it will be there. Okay. Yeah.
Thank you. Thank you.
Thank you. So the quiz will be not conducted now. It is like the end of the thing. After 5 days, maybe around maybe 17th after 3 o'clock or sometime we can have. Sure. Okay. Veera Ajay. Somebody asked. I don't know. In this, we are seeing the name only, correct? Whether it's like a student or a faculty or industrial person. So sorry if I'm not addressing properly them. Okay. Please excuse for that. Okay, so we'll take a break for 15 minutes. Now maybe I'll pause the recording for a while so that at least we can save some time. Yeah.
To all my beloved participants, we are now marching towards the second session of the day. The topic of the session is additive manufacturing techniques, to be carried forward by our keynote speaker, Dr. Kanmani Subbu, Assistant Professor in Mechanical Engineering at IIT Palakkad. Let me give a brief introduction about Dr. Subbu and our keynote speaker today. Dr. Subbu completed his Bachelor of Engineering in Mechanical Engineering from the Madras University, and he pursued his Masters on Manufacturing Engineering from Anna University, wherein he was the gold medalist in the course, securing the university first rank. He was awarded the Doctorate of Philosophy, PhD, from the Indian Institute of Technology, Kanpur. And his areas of research interest are additive manufacturing, microelectric discharge machining, laser surface engineering, conventional and non-conventional machinings. Dr. Subbu holds a high number of publications, which includes around 50 journal publications and 70 conference publications. He has a strength of 42 students under him right now, out of which 2 are ongoing PhD students, 16 MTech students, and 16 BTech students in his project. He has been the reviewer for 10 international peer-reviewed journals, and he has conducted a lot of workshops, which includes essential technique research problems and 2 GIAN courses at NIT Warangal, and a lot of technical workshops at IIT Palakkad. It's a privilege for me to welcome Dr. Subbu and carry forward this session. I welcome you, sir.
Yeah, thank you, Mr. Savanan. Yeah, let's move on to the next session, additive manufacturing techniques. I have one request to the participants that please interact with me as much as possible during the session itself. That would be good for both, because you can also learn a lot, and then obviously I will also learn a lot from you. Okay, so with this small request, I'll start my talk. The overview of the talk goes like this. We will discuss initially about what are the manufacturing principles, and then in additive manufacturing, what are the processes are there, how it is evolved from rapid prototyping to additive manufacturing. In that, we see a few applications, say rapid tooling, and then how to use this additive manufacturing in design thinking process. Okay, what is the role of additive manufacturing in product development, and then overall capabilities of this additive manufacturing process. Okay. Yeah, let's start with the basic manufacturing process, whatever you know, that is classified as a formative, subtractive, and additive. Okay, so see that this additive, it's not like a very new concept. It is there, but what happened that in 1980 onwards, when it started to gain more importance. Okay, can anybody guess why is it so? Why additive started to gain more importance from 1980s only, not before that? Is there any particular reason? I request the participant, please unmute yourself, because that is already enabled. You can unmute and then interact with me.
No, I think since 1980s, there were a requirement for any specific components which cannot be made by conventional methods, mainly in case of aerospace and space applications, because they can't risk over the mission or the project by just.
Yeah, no, yeah, somebody said that about computer. Yeah, nice. Yeah, thanks. Actually, whatever you're saying is one of the reason I'm not denying it. But again, if you think about aerospace and this thing, I think still we are not matured much in the additive manufacturing, because you may, whatever product you are making, okay, we have started to use in aerospace and automotive. I'm not denying it, but still that properties is like a question, because whatever property we are getting, are we getting a better than the conventional manufacturing processes? So that should be answered. But some other participants said about the computer. Yes. So 1980 onward, the computer also started to develop slowly. So because additive manufacturing, that plays a major role. So that is the reason that additive manufacturing started to pick up from 1980. But now, where we are now, initially started with a name called rapid prototyping, whereas now we are seeing that additive manufacturing process. Okay, we'll see that why is it like named in that way. Let's move on further. Okay, so if you see this particular kind of schematic diagram, so you can see that the subtractive format in additive, but there are some flows are going here and there, and then it is like a mutual kind of thing.
Excuse me,
okay.
sir.
Yeah, please.
Sir, your slide is not moving. It's still the first slide on.
Oh, okay. I think I'm supposed to share the screen. Okay, I'll do one thing. I'll stop sharing now, and then I'll do it again. Thanks for that information. Because sometimes this happens like this.
You can share your whole screen, sir. It will be useful.
Yes.
Yeah, now it is coming.
Yes, sir. Now it's come.
Okay.
Thank you so much.
1 minute. Now I'm in move to the fifth. Is it? Let's see, changing.
Yeah, it's moving,
Yes,
sir.
sir,
Yeah.
Oh, very good. Thank you. Yeah. So if you see that your subtractive formatted additive, okay, you take any process. It's not like a single-handed process. Like you make, if you want to make a product from the raw material, you can't say that I will do only the subtractive. Okay, there is a thing. There are some products, yeah, you need, but most of the products can be done with not only one process. It needs other process also. Why? For example, if you go with the formatting, okay, formatting like forming, casting, and all. Okay, we need a subtractive process because we need machining. After making a product by casting or forming, the surface finish of the component is not so good. That should be like to bring it to a good surface finish. Obviously, you need a machining. So that the subtractive plays a role. Like that in additive manufacturing also. After making a product of additive manufacturing, in general, yeah, people used to say that we can directly put in the application, but if you want to improve further, like properties and then say surface finish and other characters, obviously what we need is we have to go for secondary operations also. Okay, so that's why the subtractive comes to the picture. So additive is not standalone. Some products, yeah, it can be, I'm not denying it, but whereas most of the products we have to have first additive manufacturing, then you have to go for secondary processes. Mostly that is going to be a like subtractive process, machining kind of thing. Okay, so that just that I want to put in your mind. Okay, why I'm so particular about that? Okay, why means like if you see that here in this crowd, like we have faculty members and research students, if you want to take up the research, so don't go think about only additive manufacturing processing related. We have 3 steps in that: pre-processing, processing, and post-processing. You can open up your research in that side of like post-processing also. That means you make a product by any one of the additive manufacturing processes, and then please concentrate on how to like maybe make a product with a good surface finish, whether it's dimensionally correct or geometrically correct. So on property wise, is there any improvement can be done? So that kind of thing also you can think of. That's why just I'm insisting with this particular thing. Okay, since I said that in additive manufacturing, this like it is not a standalone process. It's supposed to be like attached with maybe subtractive. In that case, there are things are coming up like they have a combined additive and subtractive. Okay, so like that is the way this happens here. Okay, what you have to do, you have to make a certain number of layers by additive. After that, you have to go for a machining process. Generally, milling they'll prefer and do that. Okay, so this is the way the things are like year one slowly. Okay, so like kind of superficially discuss what are the advantages as. Okay, if people say that it's like very speed in making the things. Okay, can you just tell me why it is very, as compared to other processes, why we are thinking that that is additive manufacturing or 3D making, it's like a very fast process? For example, if you compare with the casting, we don't need to prepare a pattern, we don't need to prepare a mold, we don't need to prepare like other required things. Directly what, if you have a CAD model and then start to print. So that is the way this process is speed, and like that you have to compare with each and every process. And then it's a single step manufacturing process. You don't need to assemble after making the product, okay, or parts. Okay, here you can make an assembly. For example, gear train to be like fabricated. So that can be directly printed by this process, okay, in assembled condition I'm talking about. And then complexity that everybody knows, like making such a complex shape. For example, this shape, if you want to make by any manufacturing process, it is very difficult. Whereas additive manufacturing is called the way to make this such a complex parts. Okay, ultimately this main advantage is the customization. Okay, for example, this implants. Okay, the overall idea is the implant is like that, but the person to person is varies. So in that case, if you go for a say casting, okay, then you have to prepare everything. Whereas in additive manufacturing, yeah, it is not necessary. You can go, if you have a CAD model of that, you can make it as directly. Sustainability. Okay, that also one of the important things as compared to the other things. When I talk about this thing, we always comes from the terminologies like kind of 3D printing, prototyping, rapid prototyping, because as I said initially, that additive manufacturing initially called as prototype. Okay, so I'm just going back to the previous slide to hold that one. I like to hear from the participants. Can you just tell me what is the basic difference between prototype and model? Because both of the terms we are always use like mutually, okay? But there is a clear-cut difference between model and prototype. I would like to hear from the participant that. Can you just tell me what is the basic difference between model and prototype? You can unmute yourself. Yeah.
Model only gives the aesthetic look, I hope, sir.
Okay. Whereas a prototype?
But where it is in prototype, you can have it will satisfy the requirement.
Okay. Okay. In proper terms, if I want to put the prototype generally will make to the exact size, and then same material, it should be functional. Whereas in the model, it's not like that. Okay, it may be in a scale down or scale up size based on your requirement, and material may be different, and then it will be functional. Okay, so that is a way. Whatever we discuss now, the same thing is there in the slide. So now, if you see that model, maybe if you see that diagram here, like the picture here, it's the Google driverless car model. It's not a prototype, it's a model, because it's scaled down to a particular size and then they printed. They want to ensure certain features, whether it is working functionally, or it is possible to know whether it is fit into that or not. That kind of function only we are making in a model. So now, making these prototypes called prototyping. These prototypes should be made very fast. That's why it's called like a rapid prototype, because prototype should be made very fast. We are trying to make this with the help of these processes, whatever we're going to discuss today. Okay, so in that case, why it is necessary? Why it is necessary to make prototype very fast? Like we can make the prototype slowly also by casting, forming, and any other process. But why prototype should be realized very fast? What is the reason?
Then only the product will come to the market quickly.
Yes, yeah. Now, like it's a big competition in the market. So to meet that, the prototype should be realized very fast. Before that, prototypes made, yes, they made. How they made? With the help of the conventional process only. But once this processor are evolved, then people started to slowly use this process for making the prototypes called rapid prototyping. So I hope you understood that why this process initially called rapid prototyping. Okay, there's the reason for that. Okay, let's see that slowly then the rapid prototyping terminology is changed to 3D printing. This is basically based on the principle. Okay, so how we are printing layer by layer. Okay, for example, on a paper we are printing the maybe letters and words on that, correct? Like it's a 2D printing. So that's something, the same thing you have to do. Okay, you stack one over another and then make in one direction. That is called like 3D printing. The same thing we are doing here. Okay, so what are the steps involved in that? If you see, ultimately what, as I said initially, here if we want to make a product, we need a data of the product in a digital format. If you want to get in a digital format, obviously you need a first 3D model. After having the 3D model, that's supposed to be sliced, because we are going to make a layer by layer. Okay, each layer data we're supposed to get, so we have to slice it. Once you have done that, then what you have to do, that information you have to feed into the machine, then machine started to print. So this only generally is happening. So in that there are 4 major steps: 3D modeling, okay, data preparation, manufacturing an AM machine, and then post processors. In a 3D modeling, if you see that you have to develop a CAD model data. Okay. For example, you have a product with like you know already dimension. Okay, then you can make a model directly. But there is a product. Okay, you have only the product in your hand. You don't have dimension of the product, but still you want to 3D print it because that product made by some other process. You want to make a 3D print it. How to do? So first of all, you have to take the dimensional data. For getting the dimensional data, what you're supposed to either you have to measure or you have to do something like kind of reverse engineering on that, so that you will know what are the things are inside. So for that, we need like a 3D scanning system to scan the physical product. From that, you take the 3D model. From the 3D model, you like get a slice layer data. Okay. So in that, one more step also involved. Whatever data you're getting in a CAD model, that should be converted to STL file. That is called triangulation. Okay. So once if you have done, this is a file now you're ready with STL format. Okay. Whatever you're going to print, it's in STL format. So this data, whatever you have, that you have to check whether it is like error-free. Okay. That means like whatever you have converted all the features as it is, without any break or without any void. All those things should be checked. So that the data preparation also plays a role. So when I talk about this additive manufacturing in 3 stages, say pre-processing, processing, and post-processing. Already I addressed a little bit about post-processing. Now I will address the pre-processing. If you want to do a research, the pre-processing in one is you want to develop a 3D CAD data. That is one. So there it's a one scope. Another thing is you have a physical product. From that you want to take a data for 3D modeling. For that, how you do? So reverse engineering. What are the ways it can be done? 3D scanning is one method. There are many methods of it. Explore that method. Okay, that is another way of doing a research. It's a domain for doing a research. Okay, again. Now people are talking about this triangulation. Okay, triangulation, it's your the standard stuff where you are converting it to a data. Okay, fine. But again, now that needs are coming up like that, not only one material, you may use 2 materials, 3 materials. When the materials are like maybe more than one, how to bring that data to the STL file? That is an interesting thing people are working on. So there is a scope for in each phase. That is only I like to insist over here. Okay. Move on. Already we discussed about 3D modeling and data preparation. Now let's go to the manufacturing on AM machine. So whatever data you prepared and checked, that should be fed into the machine, and machine has to make. Again, in each machine, like for example, you consider that FDM, fusion deposition modeling machine. So there you have to check what are the parameters supposed to be like feeding, because here each and every parameter has its own significance. Okay, so based on your requirement, you have to optimize a parameter and set that. So this is a processing area. So that we have to discuss today very in depth. After that, there is another thing as I discussed already, post-processing. The post-processing we addressed only with the surface finish kind of thing. The surface finish is one kind. Apart from that, getting the proper dimension. Dimension means length. Okay, diameter of the hole, length of the component, or width of the component. This is all dimension. The next thing is geometry. Geometry, when I want to make a cube, then supposed to be in a cubical shape. If I want to make a cuboid, it should be in a cuboid shape. If you want to make a cylinder by additive manufacturing, so the cylindricity is supposed to be a proper. So what happened that sometimes due to the process, it may move has some error in the shape. That shape should be like that error should be notified, and then that error should be maybe corrected or reduced. Okay, so whenever you're talking about accuracy, we always think about only dimensional accuracy. That means we need a length, say like 100 mm length. We are worrying about only 100 mm length. Okay, but it's not only that. Okay, because 100 mm length, it gives length is okay, dimensional accuracy okay, proper. But how about the other thing? Because the all dimension joined together only giving the geometry. So the geometry is supposed to have a proper like a form. So that form error also comes to the picture. Okay, well, this is another domain to be worked out. Okay, so as I said, in pre-processing, you have opportunity in modeling, reverse engineering, and like kind of STL conversion thing. Whereas in the post-processing, we have an opening or do a research in that area related to things like whatever we discussed so far. Okay. Apart from that, there are a few more things also. That property. You want to. That is a real challenge actually. Okay. Even in the previous sessions I addressed a lot. Okay. But the properties once it is improved, or it may be showing the good properties as compared to the other manufacturing processes thing, then obviously AM will pick it up very fast. But still there is a question mark. How about the properties? Okay, because here the properties are not like isotropic, because making a layer by layer. Okay, so now this is a good time to talk. We are talking about 3D printing or additive manufacturing process, a layer by layer thing. Okay, each layer if we want to make, how we are doing, are we making a single layer in a single go? That means at a time you are making a single layer, or single layer you are making by different way. I hope you understood my question. We are making layer by layer. I'm talking about only one layer. Are we making the layer by single go? That means you are passing the energy only one time and getting one layer. Anybody?
Sir, multiple pass, I think.
Yeah, exactly. I will come. Not multiple pass. That I will come.
Yeah.
That's not by single. That is only I need. Okay.
Yes, sir.
So now we'll take example of making a cube. It has 10 layers. 10 layers means in between the layers you have one interface. So 10 layers means 9 interfaces. Okay. I will give one important point over here. Each layer exhibits different properties. Each interface has different properties. You take any property. You consider hardness one property. Yeah, consider hardness. Each layer has different property as well as each interface. For 10 layer component, you have 9 different, I can say, the regions. Okay. So 10 plus 9, 19 you have like that. In each layer you consider 10 layers plus 9 interfaces. In each and every you have different properties. Okay, that is number one. Number two, why each layer is having a different property? As somebody said, multiple pass, that I'll come to later. But when you want to make one layer, we are not making one layer in a single go. We are making a layer how? Track by track. Even track, it's not by single go. The track, we are starting with a point, then next to point. Okay, then we'll deposit the third point. We are print like a point by point. The point become track, track become layer, layer become their component time. I hope you can understand. So when I want to make a product by this additive manufacturing process or 3D printing, whatever, try to understand that if you want to make a 10 layers is okay, but you have a 10 layers, 9 interfaces. Okay, as I said, each and every layers and interfaces exhibit different properties. Apart from that, when I want to make a layer, single go, it's not a single go process. If you want to make a layer, the track should be made. If you want to make a track, first point should be deposited. So the things are happening print a point by point. When I do this kind of thing, what happens that obviously it shows different properties. That's a problem. So now something can be done for that. Really good. Now you bring a technology for making a layer in a single go. At least you will reduce the like a discrepancy in the property or variation in the property to a certain level. Okay, once you make that way, then you can plan for making even all the things together also by some other technology. Okay, so this is a way that the research supposed to be evolved related to additive manufacturing. Okay, I'll move on, then we can have a very in-depth discussion about how to think further in this direction. I like here one example, good example you can see. So it's like kind of product supposed to be printed. Okay, so this is a STL file format already like modeled and then slide and everything is ready now. So this is you want to make, okay, like thing. What is the thing is, up to this certain layer you can go. Okay, fine. But when you want to have this kind of features, which is like maybe has some slope like this, then it is very difficult to print. Because if you want to print the particular portion, what happens? It will not like stand over there. It will automatically deposit at the bottom on a platform. So it is very difficult to make such a feature. One is you can play with the orientation. Okay, that also we'll see later. Okay, another thing is, sorry, just a minute. I have to. Yeah. So what we need is, we need a support structure. You play with the orientation. Yeah, that is the one solution. Another thing is, even though some cases you can't, for that you have to generate a support. How to generate this? Again, in support generation also, you have to make a support in such a way that only less amount of material should be used. Okay. And then what kind of support material should be chosen? That is another area to be explored. And then what is the optimized support structure? So these are the conditions. Minimum amount of material should be used for support structure. Okay. Then what kind of structure should be made so that it is easy for us to remove from that product later stage. So all those things, like it's a kind of area to be explored in this additive manufacturing. Okay, so this is a process, a good example for that. You can see that here it is like printed, and then finally you have to remove the support structures. Okay, it's made by the powder bed fusions process. Okay, so once you do, then obviously with the help of any dimensional measurement equipment, you have to measure that. Here is a CMM. With the help of that, you can measure the dimensions of the printed product. Okay, so let's move on to the more insight about the process. Okay, now overall what I discussed so far. Okay, in this additive manufacturing, you have three phases. Okay, process, pre-processing, and post-processing. In each case, you have a research opportunity a lot. First of all, understand the basics. From that, you try to bring out what kind of research can be done. For that, obviously, you have to do a strong literature review. Okay. Now let's go further in that to understand about the basics of this particular thing. Okay, this is the like flow chart, like I explained about how this like additive manufacturing is classified based on the raw material. Okay. Okay, we will have a basic discussion, then I'll come back to this. I'll go back to the previous slide to keep this slide on. Okay, now your raw material only three forms. Okay, in general, liquid, solid, gas. Okay, here liquid we are using and solid we are using. Okay, for an example, can you just tell me, you have a raw material in a liquid form, but finally you need a product in a solid form. What should be done so that from the liquid you'll get a solid? I'd like to hear from the participants some answers so that we can.
So heat should be removed very fast.
Yeah, that is the way casting happens. Very good, good. But again, here one more thing, please understand, when we are talking about additive manufacturing, layer by layer, because in a casting everything is happening for a bulk material, whereas in additive manufacturing what we are talking about layer by layer, even each layer we are going with a point by point. So the heat removal is supposed to be done with a point to point. Okay, that is one thing, but again it's a challenge. Any other form?
Sir, sintering.
Sintering, it's a liquid form, correct? Your raw material is in a liquid form. How can I do a sintering? Little more, please think. Yeah, please think.
Sir, high conductivity, like you should have faster heat dissipation from the melted material to the surroundings.
Okay, no, you are all, please try to understand your raw material is in a liquid form. Okay, I'll give a resin. Polymer resin is there, your input. I'm not talking about the molten metal. I'm talking about polymer. It's a resin. It's a liquid form. From that, I want to get a solid form. What I have to do?
Sir, photopolymerization in that case.
Yeah, obviously, yeah. It's called curing. Basically,
curing. Yes.
Yeah. So in a molten metal, we say solidification, whereas in the polymer, curing. Now, the challenge here is the curing you can do. You can either add the hardener or supply some heat to that so that it will be done. Okay, but the challenge over here is how we are going to do point by point, because additive manufacturing already brought from the layer to point, because there is no additive manufacturing with a single go in a single layer thing. In that case, how I'm going to do this curing point to point? That is the challenging thing. So that is the way the process evolved for liquid base. Okay, one is called polymerization, Okay, so there we will see about a stereolithography process. Another thing they are saying that melting is a semi-solid melting. Okay, there the raw material in the wire form. That wire form material supposed to be converted to semi-solid. From the semi-solid, we are trying to get the final product. So this comes under category of liquid based. Let's move on to the another thing, solid based. Okay, the solid based here over is liquid like anyway. So anyway, let it be that process. What is that problem? Okay, solid base raw material is like a sheet form, like a polymer sheet or a metal sheet. Okay, sheet metal, that kind of thing. How can you get the final product? Again, please remember layer by layer process. Okay.
Solid state welding can be applied.
Yeah, one way, correct. I'm not denying it, but how? So that is only they are promoting with ultrasonic energy. That we'll see in depth later. Okay, there what we are doing is we are joining the material together. Okay, that is we used to say form then bond or bond then form. Those things we'll discuss in depth little later. But there is a possibility, as somebody said, yeah, join the sheet metals. From that you get the final product. Good. Yeah. Next, the raw material is in a powder form. How to get it's a solid form already. How can I get solid to solid? What can be done on that? Anybody?
Well, in case of selective laser sintering, what we do is we apply laser beam at those points where
Yes. Just sorry to interrupt. Actually, don't think in the process point of view. That's why I don't like to keep this slide. But why I'm saying is, please think in the, you have a powder in your hand. Okay, please think blindly. Because then only the research will evolve. Okay. So
sir, sintering can be done. One process.
Okay. Sorry, just a minute. Give a space for me to talk. Yeah, what I'm trying to say, you have a powder in your hand. Think like how to convert that powder into a solid form. Then you, okay, for example, I will ask the question, why laser? Why not any other heat source? What are the heating sources are there? We have like, see, chemical reaction, combustion, we can make a heat. Then we can do with, say, like resistance heating. We can have with induction heating. We can have with laser, plasma, electron. Why laser is preferred? Why not other things?
Sir, localized heating is required. So
very good. Okay, then that is the case. What are the things we can maybe eliminate from this? Okay, the resistance heating you can't do localized.
Yes, sir, we can.
No, exactly. That's like what we need. That's why, like, I'm asking you to think superficially first. Okay, then go in depth about that. It's nice that because when people are thinking about like the laser, electron, this thing are like very catchy terms to talk more. But please, what I'm trying to say, please think very from the basics, so that things will evolve a lot in the research side also. That's right. So whenever understanding the basics very well, obviously it will give a way to how to explore the research opportunities in that. Okay, that's why I like to insist more in this area. Okay, fine. Anyway, in melting, okay. So one way is powder is that you convert the powder like to a liquid form and allow to solidify, you will get a solid. That is the first thing I expected from you. So that means powder is there. Powder you convert to a liquid and then allow to solidify. So there is another solid you will get. So solid to solid conversion. What is another way? By binding. So these are the two ways are available in the powder thing. Again, even Dr. Paul rightly mentioned about difference between melting and sintering. Okay, so there again it's further in the melting. So based on this overall principles, this processes are classified like 7 processes as per the ASTM standard. We'll see what are those. Okay, one is called wet photopolymerization. Okay, for each process, if you see at the bottom, there are alternatives for that. Okay, you just go through, but anyway, like I don't like to read all the things, so I'll just read 1 or 2 for reference. For example, what photopolymerization, we say that digital light processing is other name, or continuous liquid interface production. Okay, so like the powder bed fusion process is there, binder jetting is there, material jetting is there. Then if you go further, sheet lamination, material extrusion, direct energy deposition, and then these are the 7 basic processes as per the ASTM standard. Then the last one is like hybrid. Okay, combining those. As already discussed, like you combine with the milling so that you can achieve the good surface finish at the end of the process. Okay, so these last two slides are talking about the what are the processes are there in the additive manufacturing process, plus what are the alternatives for that each processes. Okay, let's go one by one. Let's start with the VAT polymerization. Okay, what we started is there is a raw material. It is in a liquid form. From the liquid, we want to get a solid. So one thing is here I'll be giving into that it's a polymer. So the polymer only is curing. How to going to cure? You have to supply the heat. Here what we are doing, the supplying heat in a localized way, as somebody said, yeah, with the help of the laser. Okay, so they're passing the thing in a controlled fashion, so that what happened, it started to cure the or harden the resin maybe kind of say point to point. But how it is happening, that is basically a photopolymerization. The photo initiators are added with the resin. When you pass the laser light to that photo initiator initiate the reaction, and then it is allow the polymer, so like liquid polymer to become like a hard polymer. Okay, this is the overall. Now, how we are going to do? See, you understand the requirement or physics of the process. Now, how to take it as to a like making a 3D component. Okay, that is really challenging. Okay, so now if you see what is meant by VAT here, VAT is like a tank. Okay, so in a tank, the resins are like filled. Okay, so now whenever you pass the laser, okay, what will happen? It will just start to cure, you know. So now you have full tank. You will pass the laser where it will start to cure. Is it will cure at the top of the polymer in the tank, or bottom of the like a polymer material in the tank? So it depends again focal distance on many things, correct? So how much energy you are supplying to that. So now what is the thing is you have to arrange the laser in such a way that it is supposed to be there in the topmost layer first of all. Okay, fine. That is also you have done. Now what you have to ensure that you want to make a layer only. In that layer also what you have to ensure, you have to ensure that it is like now falling on only one, like say based on the laser diameter is falling only a certain amount of polymer. Okay, so that is you have to do it here. So for that, what you have to do, since it's layer by layer process, amount of layer also should be decided. Based on that, you have to have one platform. Above the platform, you have to ensure how much layer thickness you have decided. That much amount of polymer should be there on the above the platform. So the layer thickness, okay, required layer thickness of the polymer should be there above the platform. To ensure that you may have the another things called doctor's blade. With the help of that, you can confirm that like uniform thickness over the platform, as well as the required layer thickness is there above the platform. So now on the the VAT, you place a platform above that, you ensure the required amount of polymer. One problem is solved. Now what you have to do, you have to pass the laser. Yeah, you have to pass the laser in such a way that it will scan from point to point, point become track become like a layer. Okay, that you have to do. So once you do that, it's the hardened thing. So once one layer is over, what you have to do, next step is you have to go for a next layer. When you go for a next layer, obviously the as I said initially, the things are set in such a way that the topmost layer of the VAT only, it is like get polymerized. In that case, what you have to do in a platform, you have to rise one level down or one layer thickness level down. So that the challenge is coming. Your layer thickness. If I want to move this platform up and down, I need a mechanism. Can you tell me what is a typical layer thickness? A range of layer thickness generally people are adopted for additive manufacturing process. A range of layer thickness, say it is in 1 mm, 10 mm, microns, 100 microns, 10 microns. Anybody?
Sir, approximately 30 to 50 micron.
Okay, let's have 50 micrometer. Now, one layer you have done it. Now we have to move to the next layer. Now, what I said, the platform supposed to be raised, like you have to just bring it down one layer thickness, say 50 micrometer. Now you have a mechanism for the platform. okay, has a resolution of 50 micrometer. Then only things will work. So now this requirement for the way for you're making an arrangement, okay, have a platform of a resolution of 50 micrometer. So then another research thing is evolving from here. Okay, obviously we need this kind of mechanism for many things to make. I understand, I'm not denying it, but especially in additive manufacturing, based on the layer thickness, that mechanism should be made. So the platform is supposed to move up and down, rise up and down. For that, the platform's resolution, that operational resolution, it's very important that it's supposed to be around 50 micrometer. So what mechanism should be adopted? If you go with the lead screw has a pitch limitation. So once you do this, okay, once you adopt, so one is layer thickness. Now layer thickness influencing your platform operational mechanism. Okay, least count of that or resolution of that. Okay, second. And third, when you apply the laser is supposed to cure certain amount of layer, correct? That is another important thing. When I pass the layer, the laser is supposed to cure certain amount of material. I said the topmost layer in the vat, it is okay, but how much thickness or depth it will cure? So all three things are like dependent each other. You can't consider it as independent. So layer thickness should be controlled by your mechanism of the platform movement, and then laser intensity, how much you're using it, and then what kind of mechanism to confirm the uniform layer thickness over here. All three things are dependent each other. You can't consider that these things independently. So in that case, doing such a thing is not easy. Again, it is forming the way for a next level of research. Okay, so now what I'm trying to say, so once one layer is done, the next layer you have to move the platform one layer thickness down. Okay, by some mechanism you have done, good. After that you pass the layer, then started to do line by dot scanning, then dot become line, that means track or line, then it will finally become a layer. Okay, now another interesting thing is when you work on a layer, okay, it's not only exactly cure the first layer, because our topmost layer, it has to maybe influence the next that immediate bottom layer also. Then only the bonding will happen. Otherwise, what happened that each layer is deposited. But how about the joining sitting between the layers? That should be ensured. How to ensure? When you supply that laser, okay, that's supposed to even diffuse to the previously deposited layer. Then only the bonding is proper. Okay, so how many things are like involved in this particular process? Okay, so laser parameters should be chosen in such a way that it has to cure not only the particular layer thickness, it has to influence or go some more to the previously like a deposited layer. Now you have to decide how much. It is 10% of overlapping with like at the bottom, or 20% overlap, or 30% overlap, which is the best for that, and why? Because that is the interface now. I said the interface also different properties. So that is again a thing to have a greatest discussion on that area. Okay, a research on that area. Okay, so now I hope you understood the overall things involved in the VAT polymerization. Okay, what are the research opportunities related to this particular process in terms of the physics of the process. Now let's talk about a little more about process parameters. What is the thing is here laser we are using that considers the light source. It has a power, obviously. Then this laser is supposed to be scanned. So it has to, if you want to do a scanning you can do with the various speed. So the speed comes to the picture. And then the next one is the depth of focus. I said like how much the layer is going to, it is going to like make a melt or cure, that influence. So depth of focus also plays a role. That also you have to play around. Okay, now I'll ask a basic question. Now, if I increase the speed of the process, okay, how would the like kind of curing thing? So now the scanning speed of the laser is very high. Okay, that is one option. Another option is the scanning speed is very low. So where I will get a good bonding and why, or good maybe amount of curing and why? Isn't for a low scanning speed or a high scanning speed? So scanning speed, I'm giving an option that slow or high. Okay, low or high. So in that case, which one will give a better curing thing? It has to cure the polymer, correct?
I think low.
Okay, because that low decides, the speed decides that how long time you're like supplying that particular power. If it is very fast, then interaction time is very less. Whereas if it is very slow, then it has more interaction time. So optimized speed should be found out. Okay, so power is one level of parameter. Obviously, the speed also decides that how much amount of power is like going to the material. Okay, if the speed is very low or very slow, it is as many more amount of power or energy to doing the curing. Whereas if very fast, it gives only less amount of energy for a curing. So that now the resin parameters. Okay, viscosity. Okay, because that also plays a role because of the viscosity, you have to move the platform up and down one thing, and then this laser will go pass through and then do. So the viscosity decides a lot of like thing. And then leveling of resin. Already I said, like based on your layer thickness, the resin level should be maintained. The chemical composition of the resin. Not all that process parameters are affecting the process. Okay, and then printing procedure. What kind of speed you have to choose? What kind of orientation? Okay. And then what is the layer thickness it's preferred for doing this particular process. So that things and all should be optimized for this one. Here, interestingly, if you see that two things are there, one is bottom up and another one is top down. Okay. So actually, in a wet polymer, like additive manufacturing, especially in wet polymerization, what we are talking is like a macro level things, but there are things are called micro level, micro stereolithography. Okay, because wet polymerization, other name is stereolithography process. So in that you have a micro stereolithography. So here we talked about top down or bottom up approaches there, correct? Generally, bottom up approach is preferred for micro stereolithography. Okay, so these things and all like evolved based on the need. Okay, this is the major thing related to wet polymerization. The few more things I'll just say here. Parameters, what are the parameters are affecting this particular process? Okay, if you see that these are the overall properties, physical and chemical properties of the resin, and then curing depth and the cured line width, how much depth is okay. The laser diameter, like decide about cured line width, exposure, scanning speed, resolution of the scanning, that also. Because scan is supposed to have a resolution. Now we are talking about stage as a resolution. Like the scanning also, it's having a resolution. Spot size, laser power, what wavelength of laser you're using it, type of laser, and recoating system. Recoating system is like confirm that uniform thickness of the resin over the platform. Post curing process. Okay, so these are the parameters generally affect this process overall. For example, the scan pattern. Okay, because we discussed about that layer upon layer. Okay, when you go for the second layer, what happened that you should decide that how much overlap should be there with the first layer. Then only the bonding, the layer bonding between the layer is confirmed. Okay, like that here within the layer itself. When I talk about point by point, point become a track or a line. Then adjacent line or adjacent track also important. So what type of pattern should be adopted so that that overlap can be given a very good deposition or curing. So there people have worked out. Okay, this all are like if you have a system. Okay, if you understand the process very well, you can come with a proper pattern. But that pattern, only one thing, please ensure that that pattern is supposed to be like operated in a mechanically, because that is the way the scanning pattern is happens. Okay, that that the laser is supposed to move in that particular way only. So here people have explored like a V pattern, star V pattern, ACS pattern. Actually, this ACS pattern is giving a better outputs actually as compared to all. Because if you see the V pattern, it goes like this one, exactly one track over another. Okay. So, but always there is a gap. This gap is not exactly the gap that the overlap. There also it is skewed, but not to that level. But here what this is like star V means alternatively they are doing it. So that this between tracks or between lines within the layer, it is much better as compared to the B pattern. When you go for ACS, yeah, it's very, very good. Okay. So that is people like checked and then saying that this much amount of curing is happened. Here they're saying more amount of curing is happened as compared to other two types of pattern. So there's another research area works in that. So as I said, microfluorolithography, these are the few things you can see over here. Okay, you see the size, 200 micrometer. This much length is 200 micrometer. This much length is 100 micrometer. They made such a features. Okay, see the complexity of the features that possible to make by this particular process. Okay, so this is like a kind of bull. Okay, here whatever scale bar you're saying is in only 1 micrometer that made by this process. Within 13 minutes, they made this particular product. Okay, so that is the beauty of this process. So what is it? It shows the complexity. Okay, making a bull, you may ask, what is the need of it? Please try to understand the feature of the bull. So that shows that complexity of the product can be made by this process. Let's move on to the next process called powder bed fusion. Already we discussed, you have a powder. Okay, how to convert the powder form to a solid form. Obviously, you have to do melting. Okay, that means convert to a liquid form. From the liquid form, you have to bring it to solid. So this is the thing. Then now the challenge over here is powder is there. If I pass the heat energy with that, how can I like only like melt a particular powder? I don't like to like melt powder which are surrounding a particular maybe one powder particle. I want to only melt only one particle. Don't take literally one. Okay, I want to like we supposed to like melt only certain number of particles. Okay, not to all. So this control is not easy. So obviously, as compared to all heat energy sources, laser the best we can have our control. Again, whatever we discussed for the VAT polymerization, the same thing holds good here also. What is that? Here, when you want to make a layer, the layer is maybe divided into like a track or a line. Again, either track or line divided into a point. So the start with from the point. From point to point, you go further. Okay, when you do this point, like when the laser falls on a say one or two powder particle, that has to melt only that. But again, depends on the thermal conductivity of the powder, that energy transfer to the other powders around. Okay, but if you do that way, what happens? Other particles also, there is a chance it may start to melt. It may not completely melt. Okay, it may be not melt required what for the better process. No, it may like subject to heat treatment. It may start to lose its properties. So these kind of problems are there. That how to overcome. Then you have to play with the laser energy. For example, what type of laser should be used? Is it a continuous one or powder? That's it, the pulse one. If it is a pulse one, what kind of pulse you have to use? Nanosecond pulse, picosecond pulse, or femtosecond pulse? Generally, you know that in a femtosecond laser, if you use a femtosecond pulse, what happens that when you supply the energy to the powder particle, only 10 to the power of minus 15 second only you are passing it. In that case, okay, the amount of energy transferring from the laser to the powder particle, that happens during that time only. Before that energy transferring the next particle, you remove the source. Femtosecond will go away. That means that laser will go away. Then it will come for another based on your on-off cycle. So there you have more control. But how to use this femtosecond for powder bed fusion? That is a really challenge. So that you can have more control. So here, what is the thing is, again, it's a big domain to work. What type of laser is best? What laser even simply like can be maybe manipulated to make this kind of product. So now if you see that the parameters related to that, before going to that, we have to talk about mechanism also, right? So we talked about like powder to powder this. Okay. So now the powder is spread on the platform. So laser falls, yeah, melts a particular powder, or then what happens that is like become like a dot from a line to say layer. Fine, good. The now thing is, once one layer is over, you have to go for another layer. The same thing here also. What you have to do, you have to like down the platform one layer thickness level. Once it is done, again the mechanism supposed to be adopt that one. Otherwise, it's very difficult. Once it is done, what you have to do, you have to spread the powder over there. How to spread? For that, we need a recoater blade. This one. Why it is called blade? It has a kind of wedge shape at the bottom. But what is the role of that? That spreading supposed to be uniform. It has to maintain a uniform thickness. Then powder is supposed to flow. The powder itself a lot of characteristics. Okay, so generally we say powder. What we say? Average particle size. That means powder we can't get this with the same size. Okay, that means you take a powder. Okay, if you just check under microscope or check under the SEM, you have not as like all powder particles are the same size. It's a range of size you may get. That's why it's called average particle size. So in that is a case, whatever laser you're going to pass, okay, maybe if it is falling on say 10 micrometer powder, it may behave differently. If it is like a 30 micrometer powder, it may behave differently. Okay, it may require more amount of energy to melt. So like another things to understand, how much uniform size of particle you can bring, that is a very greatest thing for this process, so that it can reduce that problem associated with the particle size. Okay, so once it is done, the platform, as I said, mechanism also supposed to accommodate that layer thickness variation. Okay, the powder is supposed to be fluid powder. So once it is done, then you have to go for other things called process parameters. So we'll see that. So when I talk about laser, yeah, obviously laser power, spot size. Already we discussed about pulse duration. Okay, the frequency of pulse, all those things come to the picture. Okay, then the scanning related parameters. What are those? Scan speed, scan spacing, scan pattern. Scan speed already what discussed in VAT polymerization, you're also seeing. Now, when you do the scan, okay, that's the spacing between the scan also important, because as I said, in the one layer, if you want to make track by track, okay, one track you want to make, when you are doing with the one point, it covers certain width. When you move to the next adjacent track, that also covers certain width. So there we need some overlap, then only the bonding is happen between the tracks within the layer. If that should be done, how to do that? Then scan spacing supposed to be optimized. Again, that decides that how much of overlap you can need. So if you have more overlap, what happens that it may have a great undulation on the layer. Once a layer it not make the uniform layer thickness. So that also should be taken care. Meanwhile, you should not compromise the bonding. That also we need. So you have to choose a scan spacing in a proper way. In that way. Again, scan pattern. How to go? Can I go in a straight way, or you can go to serpentine side, or you go in a star pattern? What type of pattern is better for you to get a better output in a this kind of processes? So that is the important. Okay, that's called scan speed, scan spacing, and scan. So it's like the pattern itself, like we have a huge opportunity to work on. Okay, even IITPKD few groups are working on that. Powder related parameters, already we discussed powder size. Then distribution, you take a sample of powder in that, it is distributed. How is the distribution? Generally, it looks like Gaussian distribution, but how? Or normal distribution, we say in the technique, not technique. So in that case, how? Like in the sense, there is a set of particles are more, but maybe it's a range of particles are covered in that. Shape of the particles, it's completely random. Okay, you may sometimes you need like a spherical, so this assuming that it's a spherical, but real case is not. Then powder bed density, when you spread this powder on the platform, the density, that is like you have to ensure that we say theoretical density for powder. So here you have spread it, okay, whether it is spread like that whatever powder is spread on that, it has to like full, it is or maybe there is a gap, so that should move. Layer thickness. Okay, because the powder particle size also dictates your layer thickness, and then material properties. So that is obviously related to the powder. Then temperature related parameters. In VAT polymerization, we never worried about, but there is a powder bed fusion. What happened that when you want to have the first layer, the portion on the substrate, the substrate is supposed to be heated. Otherwise, what happens that it may like feel or experience the huge temperature difference that may lead to a distortion. To overcome that, what is suggested that you have to heat the platform so that the temperature gradient is less, so it will not produce like harmful things to the depositor. So that's why the powder bed should have some temperature while starting the process, as well as the powder feeder also. That means powder when you are depositing on the platform, the powder also has some temperature. It's not under Okay, so this is related to powder bed fusion. So when I say the scanning pattern, these are the few examples to make you to understand. Okay, layer by layer. So one pattern saying that you can go like that. Okay, from left to right, right to left, like that. This one directional scanning thing. In that, they're saying that when you go for layer to layer to layer, so there also you can play with the layer rotation angle. So this is 0. Whereas this layers, if you see 3 layers are there, okay, this is also like one directional pattern only, but each layer has different angle. So this 0 degree, 30 degree, like that it goes. Whereas this is like 90 degree layer rotation angle. Okay, now these are the things are possible. How it is affecting the property, that is a prime of. So you have to keep all other parameters constant, and then you work only on this, then only we can understand how it is affecting the final product. Okay, so this is the this is a few parameters related to that. Scan vector length. So in this case, see, it covered like it's considered it's like a one layer. Okay, the scan vector length is very more like they use like large, whereas they used half of the scan vector length. Again, further they divided. Okay, you see here like that, everything finally plotted make up 3 layers, different layers. But what is so special? What kind of difference you are finding out? People are concluding which when you go with a scan, less small scan vector length, it gives a better properties. That means that error or residual stress, all those things are reduced in this field. So one is what we talked about scan pattern. In scan pattern itself, you are very like sub parameters. Okay, those sub parameters are supposed to be optimized for the better properties to achieve on the deposit lane. So now move on to the next process called binder jetting. Okay, yeah. So now I just give a break here. I like to hear from the participant. Do you have any doubt? Until that, I'm happy to like answer to your questions. Okay. Participant, please, if you have any doubt, I'm happy to answer to your question.
Dr. Prithviraj here.
Yeah, please.
I have a doubt on the particle size distribution you were discussing about.
Yeah.
The
please.
uniformity of the particle size.
Yes, yes, yes.
So
yeah.
more uniform, is it better? Because I have a doubt on the density side. Normally,
Yes.
when we interact with the 3D machine manufacturers, they say that it's a distribution of larger and smaller sizes, so that the particle can go in between the larger particle and give a better density. So how is the relation of the particle size with density and the surface finish? Do you have any slide on that?
No, I don't have any particular slide, but what you said is correct. We can't take exactly same size of all particles. First of all, like separating that itself it is difficult. Okay, there is no proper technology to do that. We can still have a range of particles only can choose. But again, the range may be reduced because of the technology development. Okay, but still there is a range. Number one. Number two, when you want to talk about density, the packing is important. As you said, yes, small and large particles should be chosen, because again, that combination you have to work it out. What kind of thing, because the packing factor just depends on that. That small size atom go on in between the 4 large size atoms. Okay, in that case, that should be found that what range it is suitable. Okay, so now if you have that kind of packing, obviously it will improve the density. Okay, that is my overall understanding.
Okay, thank you.
Okay, welcome. Yeah. Yeah, any other questions from participants? If you don't have that, I'll move on to the next slide.
Sir,
yeah, please.
Sir, here we are looking at the scan vector length. So
yeah,
the laser or the scan is moving from one direction to another, and then it is coming back. But between those two directions, there will be a overlap, right?
Yes, yes, it is there. It is there. So here that is fixed. That overlap is fixed because here we are interested. See, this is one more point to all. Whenever you want to do a research on a particular parameters, okay, you want to know what is the effect of that particular parameter. Keep other parameters constant. But if you ask me how to choose that parameter, how to find out the constant parameter for a particular thing, for that you have to do a strong literature, or first of all you optimize that one and go, or otherwise in a given specification fix the middle value. and do the optimization. So in general, when you want to know effect of any one parameter, keep other parameters constant and do. Here, you assume it as, okay, maybe overlap is 0 or overlap is say 10%, or that you fix it. Here you check only scan vector length. That is important. So for that only the specification always helps us. That is for that only our literature review knowledge is helping us. Okay, how to fix the constant parameter for others. Parameter which other than this which is supposed to be tested. Okay.
Okay, sir.
Okay, nice. Thank you. Fine. Anyway, we'll have a end also because I just thought, okay, since I'm only talking, then I want to give a break. Okay, fine. Thank you. We'll move on. So this is even Dr. Paul covered like superficially about the binder setting and this thing. Again, here the word itself is a binder. Okay, that means they're adding the binder to the particles. Anybody can justify why they're adding the binder to that? What is the binder role of binder over here?
So that two layers of polymers get connected, and if the binding property is high locally, then we can differentiate those parts from the other parts.
Okay, okay.
Be removed later on.
Okay.
Sir, it is to retain the shape.
Sorry, just a minute. I'm getting a call. Just a minute. Sorry for that. Yeah, sorry. Yeah, now fine. Yeah, before going further, because already binder, yeah, binding to particle. But why I need a binder? I can go. I will work with the material directly. See, anyway, please remember binder will remove at the end. In a final product, you can't find the binder. So that is the thing I'm raising the question. Why we need a binder in the process? I hope you understood my question.
Yeah, sir, I think the binder will attach itself with different particles, and when we compact it and after we remove it, it can retain the shape when we go for sintering process.
Yeah, correct. But without binder also, can you do it?
Sometimes we need high energy for those materials. So to avoid.
Exactly. That is the thing. When you go with only that primary material, what happens that it needs more because it's a high melting point material. Then you have to supply high amount of energy. So now laser is okay, but beyond that, where we do electron, you may say, even beyond that, handling that laser and electron is not easy even. Please try to understand. Okay. So in that case, what we have to do is we add one more particles to that, to the main material, but it is not like going to result in the end. Okay. Here, what we have is main material, high melting point material. We are adding the binder which has the very low melting point material. So what happens that when you pass the energy to that, the binder first absorb that energy and then melt and then cover all particles, binds all high melting point particles. So now what happens? It gets a shape. Okay, if I allow to solidify, obviously you get a shape. After getting the shape, what you have to do? So now we need a shape. We got a shape. Then this binder should be removed. Can anybody tell how to remove the binder now? Because the binder first melted, like bonded all the high melting point particles. Finally, it came to a particular shape. Fine. Now that I want to remove the binder, what are the ways the binder can be removed?
So if it's a metal one, we can furnace heat it and we can burn the.
Good. So again, you heat it. Anyway, your primary material is not going to, or main material going not melt because it's high melting point material. Then what you have to do? You have to so binder. So otherwise, the binder in other form, it is like maybe removed by the chemical or maybe water soluble. That is the second thing. But yeah, you put in a furnace, it will go. So what? But what? Finally, after putting in a furnace, yeah, binder is removed. You end up with only main material. The main material got a shape. But how about the density of the product? That is the primary thing. Here, density is very low because it's highly porous in nature. Now, again, we don't want anything like highly. You are intentionally making a highly porous product is different for a particular application. But here, in general, we need a dense product. So, how to overcome this porosity problem? Any idea?
So you can apply high pressure.
Okay, that is called consolidation. Yes, good. Maybe you might have heard about isostatic pressing, hot isostatic press, heat it, and then apply pressure in all direction in equal amount so that you press it. That is called consolidation, but again, it needs more energy. Okay, so melting binder is one category. Another is very hard. Then you have to press on. Okay, that is good. Very nice. Any other solution? Good solution. Okay, another solution.
Sir, sintering of this part.
Sintering, that's why we discussed, correct? That heating that itself, it is difficult. So it may not go to that melting, that point to sinter itself. Okay. Any other? If it is within sintering temperature, yeah, it can be done. I'm not denying it, but it is generally difficult. Any other way? Still, it is porous, highly porous product. Something should be done. Any good
Particle
idea?
size could be taken very low. Like if it is in microns, we can go for nanoscale.
But still, even particle size low, also there is a porosity at the end of, because all are same particle size. 4 particles you join. There is a in center you have a gap, correct? That void is that.
So we can inject a low melting temperature material to fill the porosity.
Good idea. Very nice. Good idea. The thing is, what you have to do, you have to choose a material which is compatible one, and then it should be melted. Okay. I hope in a powder metallurgy we studied a few secondary processes called infiltration and impregnation. So infiltration, what you have to do, you have to low melting point material melt and allow this thing to like fill the holes in the porous material. Impregnation means instead of low melting point material, you take oil and pour it. So for the lubricant, you want to make a product with a certain lubricant lubrication thing, then it can be done impregnation. So here we are talking about infiltration. That means this highly porous material filled with a low melting point. How to do? That is another interesting thing. It's not like you melt and pour it, okay? What they will do, and they take a highly porous material, on top of it, they'll keep the low melting point and send it to the furnace. So what happens, that furnace heat the low melting point material, okay, and then use the capillary action surface tension, it's just fill the pores inside. So that way it can be done. So here interesting thing is the binder jetting. Your material is like the two things you understood, correct? Two things are there in that. One is binder and material. The material is spread out on the platform, and then with the help of the binder, and then you have a binder on the in a container that would be jetted. Okay, that's called binder jetting. So you will get a 3D product like that. Okay. Whereas the another one I'll cover now itself, then move on to the material jetting. That means here, like binder material is spread out on the platform, you're jetting the material. Okay, whenever you talk about jetting, that's in a liquid form. That also. So now what are the things involved? The process parameter involved here is powder, particle packing, what is the size, how it is packed. If it is you have to choose a proper combination. The green strength, because when you talk about the binder and then polymer, that kind of things are happening. How about the green strength? Okay, and particle size distribution, and then powder flowability, because it has to flow, correct? It has to spread along that. That is called flowability. We say when it's spreading, it will roll around. That is called flowability. Powder wettability, because when you pour the molten metal, then it has to wet with the powder. That also important. Okay. When I talk about a binder, it is in either material or binder in liquid form. Okay, in both the process, what I'm talking about binder jetting and material jetting. When you talk about this, the liquid metal you are jetting, okay, these are the fluid mechanics terms all comes to the picture. You know the Reynolds number, because the laminar flow or turbulent flow, Weber number. Okay, based on the viscosity, the printing saturation happens. Okay, that effect of pore size, all those things are related to this. Device parameter, layer thickness, binder setting saturation level, build orientation effect, and drop generation method. When you are getting it, it comes like a drop by drop. How the drop is generated. There itself is like different methodologies are there. Okay, this is like related to that material jetting. Already we discussed. Okay, here material is being jetted. In that case, if you see here, that more or less same parameters only, but here droplet size plays a major role. Again, how you are supplying the thing. Okay, the droplet frequency depends on the method how the drop is like formed. Drop on demand or continuous jetting. There are two methods. Drop on demand, it will like send the drop when it is required. Continuous jetting means that process will continuously jet there. But what happened, there is a mechanism, we will catch only what we need. That is called continuous jetting. Okay, then print head speed. Then material properties point of view, the viscosity, material gradient, all those things are comes to the picture. Okay, yeah. So this is related to material jetting. 4 processes we have seen so far. Then fifth one is a laminated object manufacture. That's called LOM. This we discussed. You have a sheet material. Somebody said that you can do a bonding, solid state welding. Yes. So here what you have to do, you take 4 sheets. Okay. Okay. The thickness of the sheet is like it's like equal to the layer thickness. Okay. What you have to do, you stack 4 sheets. Then with the help of the laser, sorry, but with the help of this ultrasonic consolidation method, you join all 4 layers. Once it is done, what you have to do, you use the laser and remove the unwanted material. Yeah. So what happened that here that laser is passed to cut the unwanted material. Okay. So here what is the thing is the principle called first to bond then form, bond then form, bonded by ultrasonic consolidation and formed by laser. Okay, that means the laser remove unwanted things by decupping process, because it will like take it as like a cube thing. That means it will not just like that cut rectangle panning operation. Instead of that, it will go like it will laser skin like cell by cell. Each cell will be like removed. That is called decupping operation. Okay. That is done by the laminated object manufacturing. So first of all, they will take 4 sheets, attach, ensure the bonding, then they'll form by the laser. Okay, this is called bond then form. There is another way called form then bond. That means you make first a form. That means you cut the sheet to the shape first, then you bond it. Okay, that is another laminated object manufacturing, which is preferred, which is you have to decide based on your product what you need. Okay, so here not only the ultrasound, there are many methods you can go by gluing or adhesive bonding. What is the problem with the gluing? You can't have the uniform thickness. Okay, another thing is you can't get the proper strength also. Then another way is thermal bonding processes. Okay, thermal bond like you supply the heat to that, then it will bond. Then clamping, mechanical clamping. So there are many methods, but ultrasonic is the best one. So these are the process parameters. Okay, like here, since we are talking about ultrasonic thing, oscillation amplitude, how much force you are applying, and then that sonotone, whatever you are using for this process, the travel speed of that, and then here also temperature is important. So preheat temperature. Okay, so here once you do the process, like the quality should be ensured. How to ensure the quality? That is called linear welding density, LWD. So this is like 4 layers. As I said, 4 layers bonded. Okay, you see that here some dark marks. Okay, layer 1, layer 2, layer 3. So whereas white at that particular interface, that means it's bonded properly. Whereas these darks are there, it's like improper bond. So what is the thing is here that shows that the percentage of interface which is bonded divided by the total length of the interface. That is called linear welding density. That is the parameter helping us to qualify this particular weld. Quality of that particular UC bond weld checked by this. Okay, so this is you have to do obviously with the optical microscope. Okay, cut the sample and then check that. Okay. So as I said, these are the 4 parameters. Let's see that. Okay, anybody can tell me, okay, oscillation amplitude, if it is increase or decrease, because at least for one process we can discuss some more about the process parameter. Anybody can tell, if I increase the oscillation amplitude, what happens then? Okay, it is like high or low. Can you just tell me how it is going to affect the bonding of the sheets? Okay. Anybody? So that ultrasonic thing is the oscillation amplitude is that it is low or high. If it is high, what happened? If it is low, what happened? If it is low, obviously you will not get a proper bonding. If it is like, it may influence other layers also. Okay. So here, that's why the optimum energy should be found out. Okay. That is depends on what geometry you are going to do, what thickness you are going to do with it. The quality of the weld is ensured in this way. Normal force, yeah, force is needed. You have to hold this like layers and then you do the ultrasonic consolidation. Okay, that ensure that the metallurgical bond between the layers. Again, if it is higher or lower, then this bond is not proper. It leads to a degradation. Okay, that dictated by that lower welding density. Okay, sorry, linear welding density. The travel speed. This is already discussed. If you have a low speed or high speed, High speed means you have only low welding time. Okay, that means the bonding between the layers is less. Whereas if a high, then if it is a low, it is more. So again, that also should be optimized. Otherwise, what happened that you may not get a proper weld. Pre-temperature. Again, that also if you increase or decrease, that dictates your finally linear welding density. Okay, because this pre-temperature dictates the flow stress between the okay. Again, when I talking about sheet, what are the things that we are like here to try to up to like 150 to 200 micrometer thickness can be bonded with by this process. This is especially aluminum foil they have bonded. Okay, so this is I just keep on saying ultrasonic consolidation. This is a typical figure for that. So these are the foils or sheet should be like bonded. Okay, this is the sonotron. This is rotating in a particular RPM as well as this oscillation also. Okay, so that gives the particular. Now, in this, apart from the parameters, I like to address few more things are application. So, with help of this, because when you talk about this IoT, when you talk about smart machines or smart manufacturing, digital manufacturing, we need many sensors should be embedded. Okay, so among all 7 processes, ultrasonic consolidation is providing a lot of solution for that. Okay, so here if you see that internal features, if you want to make. Okay, what are the internal features? For example, you want to make a hole, okay? It's not like a groove. If the hole is there in the middle of the product, that also it is not like kind of, it is horizontal to x-axis, not like a, so it's an x-axis thing. How to make such a hole? Okay, because in a 3D printing or in additive manufacturing, you know, if the hole is there, above that hole, if you want to deposit any layer, where it will deposit, it will fill the hole only. You might not get the proper hole. But by this process, you can make any internal holes. Square holes can be made. Honeycomb structures can be made. Enclosed cavity can be made. Pipes can be made. Internal hole, hollow like that you can make. So that is a possible over here. Okay. So because how you deposit it, you join the sheets, but use the CNC to mill it. Remove the thing, so we get the features out of it. Okay, that is the way this internal features may be made. Material flexibility. You can combine the different material. Okay, you combine the aluminum material with inconel or brass or stainless steel mesh. That can be done. Okay, so maybe you can see the next thing. See here, there are 2 aluminum layers. In between, they kept this SS mesh. So this kind of flexibility is there. Why I need, okay, there is a particular demand that it need more stiffness. For that purpose, in between aluminum, they kept SS mesh. So they want it don't kept by additive manufacturing, especially not this laminated object manufacturing. It's possible. See that the bonding with the help of SEM, people have even checked that also. Okay, so that is the next one is a fiber embedment. When we talk about that, IoT, so you want to have the data, how about the machine, the digital twin, and all those things you're talking about. Okay, I know I want to fetch the data from that. So for that fibers, if you embed with that machine, that is great. How to embed? This way it can be embedded. For example, powder bed is there, like in a lathe machine tool, bed is there. On the bed, for now, I want to get the information how much load that bed is withstanding. Okay, for that I want to embed the fibers while making like making the bed. That can be done, but ensure that if you make a bed by additive manufacturing, it is good for a lathe machine tool or not. Okay, so that kind of thing. So again, you can dictate which direction it should be done. Okay, so this is called fiber embedment is possible in this process. How they embedded in between the aluminum layer they embedded. Okay, see that thing. Okay, so the silicon carbide thing they were embedded here. The silicon carbide fiber they embedded. When you do the embedded like that, see this is in between same material. Okay, but whereas here it is like kind of 2 different material. When you do this thing, because of the copper and the aluminum, they have different nature. The extrusion kind of thing is happened. That means when you insert this fiber, what happened that this material over extruded over that fiber. So again, it's again interesting things to be worked out. Okay, smart structures. I want to embed the sensor directly to the machine. How I embedded these this kind of fiber, yeah, that can be done. See this process here. So this is a material, okay, one plate kind of thing. In that, they're embedding the sensor. Okay, they place the sensor. Now they close with this layers. Okay, sheets, and then finally close. Now that sensor is embedded finally inside the thing. So now the panel has the sensor completely. You use this one for any machine so that you can fetch the data of that machine. So that can be done by this. So another process in additive manufacturing thing is called material extrusion. Your raw material in wire form, okay, polymer wire. Okay, what you have to do, you have to take another solid, you have to bring out of it. Then you have to convert a liquid form. But here instead of liquid, semi-solid form you are making. How you are making the semi-solid form? Here, what is the thing is when you there is a extruded with a nozzle. Okay, in the nozzle you have the pulling system. Okay, that wire is pulled between these two pulleys. Okay, so the wire now pulled inside. Here you have a heating element. Okay, it will like by the resistance heating, this wire is like heated, then it pass through the nozzle. So now the nozzle you have to dictate in such a way that what type of product you want. Okay, here many things comes like build orientation, layer thickness principle. This all are regular parameters, whatever is seen in others. But here interesting parameters is infill density. What is infill density? This is a process dictate that when you want to make a product, maybe decide how much amount of material should be deposited inside. Okay. Okay, before going to that particular infill density, these are the key features looked into this fused deposition model. How to load the material. Okay, these are areas are available for doing a research. Okay, how to load a material. I said 2 pulley systems only. Like now, I said that it is fused through a nozzle. Okay, how the pressure is determined? The pressure is determined by the speed at which the material is pulled inside the nozzle by the pulleys. So the loading of material has many like opportunities to check and then bring out a new liquefaction of material. We brought the, like I said, semi-solid only we are making with help of the resin. What are the other methods? Okay, application of the pressure to move the material through a nozzle that I already said through the pulling of pressure only. Then extrusion, because you are throwing the nozzle, you're extruding out. Okay, and then plotting according to a predefined path and controlled manner. How we are going to do plot, that we will see in the next slide. Okay, bonding of the material to itself or secondary build material to form a coherent solid structure. When you have 2 materials, because this is again opening a venue for joining 2 materials. Okay, we want to make a product with 2 different materials. Yeah, there is a possibility. You may say binder, but binder you're removing at the end. But here, purposely, intentionally, we are adding to material and get the product. Okay, so support structures also should be generated. For example, this is a product should be made. Okay, how can you make such a overhanging structures? So generally we play with the orientation, correct? So if you want to print like this, you need a support structure, or if you print in other direction, you need again the support structure. But if you do upside down, you don't need a support structure. First of all, you play how much is possible with the orientation. You reduce the support structure, or you try to eliminate the support structure as much as possible. Okay, then not possible, find out the orientation in which you can have a less amount of support structure, and then you choose a support structure material in such a way that it should be easily removable. Okay, and then there is a condition. Okay, if we have overhang like less than 45 degree, no need of any support. Okay, so it's not all overhang needs, but again certain degree of overhang is important. If you have more than 45 degree, then it needs a support structure. So what happens over here, the less than 45 degree, the previous layer acts as a support structure for this thing. If you have a overhang less than 45, whereas if it is more than that, the previous layer don't have the material to support for the more than 45 degree deposition of overhang. The plotting, as I said, here it is interesting that when you want to make a feature, which one will you print first? Here, FDM, outside should be filled first. The fill. This one, the plot outside you have to put. Another thing is, whatever pattern you are choosing, you have to choose a pattern in such a way that reduce the number of turns. Okay, so don't take any drastic thing. So in this way, if you do, they find that there are 3 fill patterns. You see this one. Okay, this is a fill pattern 1, first one. Up to this is the only fill pattern 1. Okay, it starts from here, goes like this. Okay, goes like this, and then going like up. So this covers the one fill, this portion covers the fill pattern 1. Okay, whereas the second one starts from here. It starts from here and goes like this. It goes up to this. Okay, So one fill pattern, second fill pattern, the third fill pattern only this much, small one. Okay, they chosen 3 fill pattern. With help of that, they try to cover. They're trying to reduce the number of turns. Okay, that is the reason they are going with that. Another, sorry, yes.
Sir, I was asking in the previous slide, you said that for angle less than 45 degree, we don't need any support, but does that not also depend on the protruded length of that part? Because if the weight of the extended part is too much, then it will fall.
Yeah, good question. But please try to understand, if you want to go, it's like length of the overhang, but you think the topmost portion of the overhang, okay? But still you have a previous layer, correct? The previous layer still help you to support that one. So why we don't want, don't need a like less than 45 degree any support structure means because the previous layer always act as a support structure for that. So that is the reason. Your length of the protrusion is, but angle of protrusion is important. Okay.
Okay, sir. Okay.
Thank you. Thank you. So another interesting thing is this should be noted clearly, because when you talk about the overturn, I said correct. Why you try to reduce number of overturns? Okay. Why means what happens when you are taking a turn, the nozzle will take a turn based on the relative dynamics. Like for example, it is going and taking a turn. Okay. So what happened that time the relative velocity becomes 0. But whereas the whatever is oozing out through a nozzle, that still continuously coming out. Certain velocity is continuously coming out. That is the reason what happens that when you take a turn, it is depositing more. You see that any particular this kind of scanning pattern you choose, especially when you're taking a turn, there more amount of material can be noticed. Okay, that is one thing. And another thing is when you talk about the depositing outer layer first, and then you are planning the scanning pattern within the layer, within the border, then what you have to do, this gap also should be taken care. Okay, there are also some overlap. It's not only that overlap between the layers or within the layer. Okay, even within the layer, outside of the border also you should take care of it, because that is also decide that void and everything. So as I said, infill is one of the interesting parameter in the FDM process. Okay, because it dictates that. See, porosity, we always say that it's like kind of unwanted thing, but porosity also need. For example, in a bioimplants, you need a porous structure. So that porosity also like kind of not a random porous. It's like kind of uniform pattern of porous. So that can be dictated by this process. That is the beauty of infill, this thing, fuse deposition process. So here you see that different thing, 100% the thing, or it's 0% infill density. Then slowly they're increasing. Okay, you'll get the full also. Okay, you can see here, and 0% it is going slowly. This is a pattern they follow. Okay, that is how it is happening. So as I said, where in the scaffold architecture, because I need we like scaffold should be made with a certain porosity, because it need a porosity more than 66%. Why I mean then only this the cell will go deposit, culture, and this thing. It needs a space. For that, the scaffold made in such a way that with high porosity. Okay, this is the one important point. So that's why that leads to what biomedical related implants. Okay, like if you see that all implants, if you want to make there, especially for this, say, this particular portion is like prone, and this and the human face thing. So that can be like replaced with the implant. So the implant is supposed to be made to the sex. So you have to 3D scan it. After getting a 3D scan, you print a particular thing and then attach. Okay, I already said the human structure when you want to mimic these human bone structures or not. So that made with highly porous thing. Okay, so that all like all implants like first of all customized, and then some implants need with the highly porous structures, because that only that cell go and culture over there and then have a proper bonding with the body. Okay. Okay, so these are the few examples. This is a material made by electro beam melting also. So in another important process, because laser we are using, like the electron beam also used, that is called electron beam melting in additive process. Sorry. So these are the other factors are affecting input pressure, temperature, nozzle diameter. So these are the things we not covered in that. Okay, these are the related to FDM process, fusion deposition. Move on, maybe it could be the last process. Okay, direct energy deposition. See the direct energy deposition. Again, it's powder only. Powder you just convert to liquid form and allow to solidify, you'll get a solid again. So the principle, the one principle powder bed fission is spread on the platform. Whereas here, with help of the hopper, you are passing the powder and then the laser pass at the exactly center. It's like a concentric nozzle. Okay. Okay, so the center of the nozzle, that laser comes through. Whereas the surround that nozzle, you have the another nozzle. So through that, you get the powder. So both will meet at a point, maybe above the platform or exactly on the platform, and then like melt and deposit. So that is called direct energy deposition. Okay, these are the parameters related to that. Not only the powder, metal wire also can be. How we are used the polymer wire for FDM, here metal wire can be used. But again, the melting point of the metal wire is important because it may work with only low melting point. Otherwise, you have to supply more amount of energy to melt and deposit. Okay, again, it's an interesting thing to know. So another few more things to superficially I'll cover. Maybe in the next talk I may cover about more. Okay, this technology, whatever it like discuss on process related to ASTM additive manufacturing processes. Okay, it has many applications. One of the applications is repairing. Because see, this is combustion turbine burner. Okay, this burner it is like made up of high temperature material, and then it has to withstand high pressure also. If it is worn out, what happens? You can't just like that throw it. Okay, if you repair, that could be used for further. So the repairing, if you want to do that, repairs do in such a way that it's look like a new material. But anyway, that cannot be done. But at least you have to go to the near to the level of a new product. That is possible by this additive manufacturing process. Okay, so this is like SLM process can be used for adapted for that. It is 10 times quicker than the generally traditional repair methods. Okay. So for not only that, even turbine blade also, the blade you can see here, it's a turbine blade. You need the shape of the blade, you can understand the shape of this figure. It has some mini holes also, small holes, and many holes are there. Okay, that is for air cooling purpose. Okay, making such a hole is not easy first of all. So this is a worn out turbine blade. Okay, by this additive manufacturing process, the turbine can be repaired, then can be replaced. Generally, what happens if it is worn out like this? We are throwing out, we are scrapping it. No, it should not be. It can be reused. But the problem is if you do a repairing, but the repairing is put in a good level, otherwise it can't be used as new product. So, but additive manufacturing part the way to some extent that it can be used as a fresh product. Okay, so these are the few things related to that. What are the processes involved in this repairing work? For example, what are the things people have tried? Turbine blade I have shown now. Die people have repaired. Engine they have repaired. Rail and apart from these 4 applications, there are others 20%. So these additive manufacturing are helping because die making are not easy. You have to spend a lot of money and then you have to wait for a long time. So if you have a repairing technology in a better way, it's really great maybe application for the industries. What are the process? Generally, they are using direct energy deposition only. They are using for repairing purpose around 86%. Maybe other processes also. If it is a polymer, we are going with FDM. Metal means powder bed fusion. Even polymer also can be done by powder bed fusion. Another interesting application is rapid tooling. This we can discuss in the one lecture. It's called soft cooling and hot cooling because the die is made by hard material as a soft material. So this tools can be made by solid materials. Okay, so that is a interesting thing by additive manufacturing. Okay. This I'll just cover in the maybe next lecture because since we have a less time. Okay, this particular part I'll cover in that one. But this is a design thinking. How it is helping the design thinking? Okay, can anybody tell the truck now got stuck between the road and the bridge? Can you give an idea so that without damaging much, the truck should be like moved away? So what can be done?
So rotate the protruded part by a certain degree so that it can.
No, you did not understand my question here. What I'm trying to say is that please listen. Like here is the truck. Okay, truck got stuck between the road and the bridge.
Deflate the tire.
That's all.
Deflate the tire.
Puncturing a tire.
Yes, that is only because that is like generally will not be all what we people generally think. Okay, you just like maybe whatever this bridge part is there, maybe you remove it or otherwise you cut this part. Something they'll say. Okay, but out of box thinking is important. So that deflate tire is possible, but there are something you may think, oh no, it's a nonsense idea because there is no manufacturing possibility. That's why some ideas are like restricted. Don't restrict. Even if it is a childish play or it's like, don't worry about that. Please have the idea. And then, so now additive manufacturing thing, even what you thought that is not at all possible by any process, that is made, this additive manufacturing made that as possible. So in design thinking process, it played a major role, you can say. Okay, this topology optimization. See what happens due to the optimized like manufacturing process, unnecessarily spend more amount of material. That material we are not using even effectively. That can be effectively used for many processes, but because of that manufacturing process limitation, we are unable. But now we are able because additive manufacturing for the way, because complex shapes also can be made. Ultimately, what I need a support to like I need a shape like to support the structure. That can be made with this. Okay. So like kind of a model thing. Okay, you modelize and do. So this already we discussed. This kind of topology optimization. Initially, see, we need only this shape, but due to the manufacturing process constraint, we made like this. We have been using for a long time. Now this is called topology optimization. This you need the system and the license software. We can work a lot on this. It's another area. Reverse engineering already we discussed. I'm just skipping ahead and see the complexity. This kind of products can be made and prototypes can be made in a rapid. Okay, again, this for the way for kind of things. Initially, this is made by the conventional manufacturing process, and then they would like extruded the sheet metal. From that, they got the skeleton. But now, see the skeleton shape because this additive manufacturing thing helped us to make such a shape. So overall, in a nutshell, what I want to say is the journey started with this thing, making a rapid like prototypes in a rapid manner. That's why it's called rapid prototyping. Okay, making only models and prototypes. Whereas that slowly it is evolved to you repair the product and then we started to use in tooling. But now what is happening? We started to use this as a final product, number one. And apart from that, this additive manufacturing like process, like explore in all materials. Now, extensive research is going on metal. So started with the polymer, slowly moved to the ceramics. Now we are working very extensively on metal. So since, as I said initially, started to use as a final product, that it's called additive manufacturing. Okay, initially it is only making of a product. Now this process evolved as additive manufacturing. Okay, so where we are going on, like see, this is a chart talks about 2016 to 2027 market prediction. In 2027, like you see the demand for the each processes, huge demand is there. Where we are now in 2021. Okay, so see that each color represents particular process. Okay, if you see the dark thing that represents that particular process. Okay, so it requires the things. You know, when the selective laser melting represented by this one. Okay, there is a huge demand for that. So if you want to do a research in additive manufacturing, you choose any area, work it out. There is a like a great future there. How about the market potential to have an overall idea? You see the market potential, like it is like stacked in that base the requirement. The consumer uses like it's more. Okay, that's why at the bottom. Whereas in the tooling and molds also we are using it. That is in the from the top second. Okay, but product manufacturing we are using also more because of that. As I said, we have started to make a final product out of it. Okay, even we are using in medical. So in most of the hospitals nowadays, they are having 3D printer in the operation theater because it is helping the doctors to understand what is that. They have a MRI scan that gives feed to the machine and then print it and then understand properly. So where is the damage? Where is the problem that we can understand and then work it out directly. Okay, so that is a way. These are my references. So thank you from my side. Yeah. So herewith I conclude my session. Now session is open for questions. I am happy to address your questions. Hello. Am I audible?
Yes, you're audible, sir.
Yeah, some answers. Yeah, fine, good. So if you have any questions, yeah, please answer questions. Already we discussed in between. Okay, I understand that. Okay, and then more or less is lunchtime. Everybody is very maybe feeling angry. Okay, but still we can have a couple of questions so that I can mind if you want. Or you can write your questions also here.
Sir, actually, when I asked the question about scan vector length,
yes,
I mentioned that there will be an overlap. What I wanted to ask is that in the overlapped position, there will be a difference in properties, right?
exactly. That leads to different property. But that overlap here considers the interface. Okay.
Okay.
Okay. So what are the reference and the textbook to start with, sir? Okay, there are some basic books. Even Dr. C.P. Paul has written the book with a student. Actually, that is a very good book. I have gone through that book. It's really good because he has written how our Indian people are go through the things. Okay, based on that only has written. It's like covered most of the things. I think I can maybe recommend that book not only for the researchers, even for the student who are doing BTech or master's secondary. They'll get a very fair idea about additive manufacturing process. Yes, maybe I can share some more books maybe a little later about the details. Sure, that I'll do. Yeah. Any questions? In a DED process, which gas is used as a shielding gas, particularly? Generally, they'll go with the argon because inert gas is necessary. Otherwise, if you go with other gases, it's mainly prone to oxidation. Okay, that is important. Like generally, they'll go with inert gases. Vijay Kumar, that is my. Yeah.
One question about the that angle slides.
Sorry, sir. One question.
There was an angle and overhang.
Yeah, please. Yeah.
Just confused. Is it the other way around, or can you just take that slide?
Yeah. Just a minute. I'll go there. Sorry, I'm just going slowly. Yeah, here. There's the one you're talking about.
No, this one.
Yeah.
Okay, so if overhang 45 degree, if less than 45 degrees, support is needed, isn't it?
No support is needed because it is previous level of support to that, correct?
No, I mean less than 45 degrees means the angle is very small, so it will not support. Otherwise, if it is vertical, it is. I don't know. I was saying.
Okay, please check it once. But based on my knowledge, this is the thing. I will also check it since you raised that issue.
I mean, okay, the angle where it is measured. Okay.
Maybe. Okay. Fine. Yeah. Good.
Okay. Then.
Okay, I'll check it also. We have even one participant saying that. Okay. Fine. Good. Thanks for that. Maybe I missed that one. Okay. Yeah. Any other questions from the participants, please? Yeah. Any other questions? Because already one because we have to meet at 2. Metal powder size range can you tell me? Metal powder range, it's depends on the process what you're choosing. Already we discussed, correct? We get not only, see, if you want to say 30 to say 45 micrometer range, because what happened that we need a big particle size as well as small particle size. Then only what happened that the tacking will happen properly. Okay, so again, if you go more than that, what happened that it is very difficult to spread the powder also. Okay, the spherical shape is also important. We are assuming it's spherical, but generally it's not so. Okay, so if you go for a larger particle size, then that shape you can't get the spherical shape just like that. So then that case by spreading by recoater plate is very, very difficult. Yeah, that is one thing. Yeah, I hope I answered to your question. And then melting type powder bed fusion, that is after melting the powder particle, is there any specific method to control the flow of liquid metal powder? Yeah, you have to play with the process parameters. Okay, again, that gas flow also is important. That also like a thing. And then the see what happened that the metal pool dynamics is important. Okay, so that is only dictates a lot of things for bonding with the previous layer and adjust layer and all. Okay, that should be taken care. So regarding the fusion, obviously multiple dynamics should be known. Yeah.
Hello, sir.
Yes, please.
Sir, I have a very generic question. Like, sir, I have recently completed my master's in mechanical system design, sir.
Okay.
So now I want to pursue my PhD in this additive manufacturing, sir.
Okay.
The thing is, right now, like I have been studying very basic few additive manufacturing processes from a month, and I have been attending certain these FDPs like IIT Kanpur have been scheduled that before this IIT Palakkad. So the thing is, like, I'm getting more interested in this additive manufacturing. Is it like for my PhD, do I need to go for internships or any project opportunities before joining the PhD, like so that I can go get very
okay, I understand that. I understand.
Yes, sir.
Okay, see, generally what people generally prefer that if you have done that in masters. See, if you want to pursue any particular topic in PhD, if you have done that kind of work in masters, then it's easy for the candidates as well as the guide for take it forward. Okay, but it's not like mandatory thing. Okay, you are interested, it can be learned after joining also. Don't worry about that. You join and do the coursework. Slowly you'll start from this, correct? Because since you are attending many workshops, so I think you can have a fair idea about what is happening right now. Okay, so to have the whole, like what people have done so far, obviously you have to be a literature review strongly. So after joining any PhD program, then you have a time, 6 months, 1 year, time is there to do a strong literature review. Again, the literature review is not going to stop within a year. Throughout your PhD, you have to do a literature review. Okay, there is no end for it. Once you start the thing, you have to keep on doing a literature. In that case, okay, it is important that you should have an interest to do that. That's all. No need of any basic eligibility, or you have to go for any training, or not necessary, in my opinion.
Okay, sir. Like I have, my project was based on this surface composite, sir.
Oh, okay, nice.
Yes.
Friction. How did you do by friction stir processing?
Yes, sir. Yes, sir. I did by means of friction stir processing, sir.
Okay, so now even you take that one forward. Okay, from that, is it possible to do additive manufacturing? Like it can be in friction stir processing. Many things are there. Okay, or friction stir deposition also there. With the help of that, can you do additive manufacturing? So because you have already about friction stir processing very well. So in that, how can you take that kind of process to the next level? So if you bring additive manufacturing, that may add already people have been working on, but still it may give a new avenue for that. That's my understanding.
Okay, sir. Sir, there is a one process like friction stir additive manufacturing.
Yeah, then it's good to have. I heard about that. Yeah, it is there, but people are like started, I guess. It's not like, see, in EDM also it can be done. But the problem is after going certain layers, still you're able to make layer by layer, because one layer you can make, second layer you will do in. How about the first layer? Whether it will be there or it will be removed. So many questions are there. So the
yes, sir. There is a yes, sir. We cannot manufacture these complex shapes in that particular.
No, that's a lot of limitations. So how
yes,
to
sir.
overcome that? That should be done actually. Okay, there are many interesting things are there. See, we can't make one process for all. That is not
yes.
possible. Okay, this is a general thing. So you make one process for a particular thing, it's okay. When you talk about mass production, obviously one dedicated process is enough. If you know that it is not mandated that one process should address all. Okay, that is, we have generally, that is our problem, I think, as a researchers, or maybe industrial people are expecting that if I have one, that should be a solution for all. How it is possible? It is no. Okay, no
sir,
problem. So we
sir,
that.
Sir, the thing is, like, I have been approaching since, like, I have applied for IIT Delhi, IIT Madras for these additive manufacturing positions and for PhD, sir. But as of now, like, I was shortlisted after getting the written examination. But as a thought of, like, sir, in the interview thing, sir, like, it was 80 to 90% was very good going, and 10% was like I was lagging in some technical or questions, sir. But the thing is that I am not getting the position right now, sir. What should I do for this thing?
Okay, this is we have to talk personally. It's not a forum to discuss right now. Okay, because I have a couple of questions. We will discuss, sure.
Okay. Thank you, sir.
Don't worry. We'll have an interaction with the participant that we can do. Yeah. So there is one question. FDM and sorry, I'll go to this chat box because FDM and metal 3D printing. Some other also questions are there. Okay, I missed something. Yeah. In melting type powder fusion, that is SLM, after melting the powder particle, is there any specific? That is we discussed, sorry. FDM and metal 3D printing of 2 into 2 cross 2 centimeter cubic, which method is printing faster? Okay, FDM or metal? If you are saying metal 3D printer. So I may consider that metal you are talking about. In that case, FDM push deposition model, generally we are going with the polymers. You want to print from the metal wire, then you have to go for wire arc additive manufacturing. Okay, number one. If I compare this wire arc additive manufacturing with the metal 3D printing, say SLM kind of thing, SLM is faster. Okay, because the laser you're using it, correct? So in that way, that is a faster thing. Right, good. Yeah. So I'll move on to the next question. How the infill percentage influence density after centering of ESS material points? Okay, so can you like tell me how to calculate the or measure the density? Okay, so is there any weight of the material plays a role? So you think in the direction, you may get an answer. Okay, yeah. Let's move on to the next. Injection mold components can be produced with metal insert should possible for complex component, but it should be 3D printed. Okay, see here when you talk about insert, please try to understand not only this application. I'll give an overall thing. When I see by additive manufacturing, we can make many parts or any parts, like I can say, but the problem is, for example, insert needs some particular properties or characteristics that should be there. By additive manufacturing, you are unable to reach to that. You make a product, whether it is achieved the required properties, then that is a question. If it is not so, then you can't use this one. Okay, so